In this lecture, what we'll be doing is we'll be solving a couple of example problems involving the Rankine cycle, and we'll begin by looking at a simple Rankine cycle just so that we get some practice at solving these types of problems. So there's our problem statement. What we're dealing with is a simple ideal Rankine cycle, and we're told that it's operating between the pressure limits, the boiler pressure at 3 MPa and down to the condenser pressure of 50 kPa. We're told that the steam at the inlet to the turbine is at 400 degrees C, so that would correspond to the 3 MPa boiler pressure. Now the mass flow rate is given at 25 kilograms per second, and we're asked to do a couple of things. One is to show the cycle on a TS diagram, which is always a good idea to be able to figure out what's going on with respect to the saturation lines. The second thing that we're after is the thermal efficiency of the cycle, and finally the net power output. So that would be a power output in megawatts. So that's the problem that we have before us. And whenever you're doing these types of problems, it's always a good idea to begin by writing down the information you know, and we will also write out the TS diagram. So let's get started by doing that. So that's the information that we have before us. Now looking at the TS diagram for this cycle, it's not too complex. So we write our two-phase line for the cycle. And remember, we always start at the compressed liquid region over on the left. That is state 1. We go through the pump. That takes us up to state 2, which then goes into the boiler. We follow the lines, and we go into a superheated state. That takes us to state 3, and then we come through our turbine and we expand to some point. Right now, we don't know where we are expanding to. It could be superheated, it could be right on the saturated vapor line, or it could be in the two-phase region. And so that will be state 4, and that takes us back into the condenser. So what we'll be doing here, whenever you're solving one of these problems, it's a bit of a puzzle that you're solving. And you usually start, like any puzzle, you start with the conditions that you know. So consequently, what we'll do, we'll start at state 1. And we'll go into the steam tables for that. And so what we'll do, you go into the steam table, and here you would be looking at saturated liquid or saturated water. We know this here is at 50 kPa, and this here is at 3 megapascals. So you go into the saturated, or the steam table, saturated liquid, 50 kPa, and you pull off the enthalpy. And I'm going to skip the units, but that would be kilojoules per kilogram. And another thing to pull off at this point, let's get the specific volume. And after you do a number of these problems, you'll know which things to pull out of the steam table at which point. But you'll see why we want the specific volume in a moment. So that's the specific volume at state 1 as well as the enthalpy. Now, we have a pump which takes us from 1 to 2. At the initial state here, we have no idea how to estimate what state 2 is, but what we'll be doing is we'll be taking advantage of our reversible steady flow work equation, and that enables us to say the work in the pump is the specific volume at 1 multiplied by the change in pressure between state 2 and state 1, and that is equal to the change in enthalpy. So by knowing the enthalpy at state 1, we can use this equation in order to determine the enthalpy at state 2, because if we look here, we pulled this off the steam table, and we know P2, that's the boiler pressure, P1 is the condenser pressure. So we know everything in that equation. We also know H1, and that enables us to get H2. So when we calculate this, what we find is the value is 3.0385, and again that would be kilojoules per kilogram. And so we can sub it back in and solve then for H2, and when we do that we find that H2 is that. So the next thing to do, we have state 1, and we've figured that out. We figured out state 2. The next place we want to go is to state 3. So in order to do that, what we have to do first of all is determine, are we superheated? And so you go and you look at 3 megapascals and 400 degrees C. Are you in a saturated region or are you superheated? And for this case, it'll be superheated. So that takes us to state 3. So you pull out the value of the enthalpy there, and let's pull out the entropy. We're going to need that, and I'll show you in a moment why we're doing that. And that would be kilojoules per kilogram Kelvin for entropy. It's different than enthalpy. Now, state 3, we just pulled off the steam table. It's superheated. Now we're going to use the value of enthalpy there in order to figure out where state 4 is. Right now we don't know where it is, but we know the entropy, and we can say, or assuming that this is going to be an isentropic expansion process in the turbine, we're told no different. That enables us then to get a direct link between 3 and 4, because we can write entropy at 3 is equal to entropy at 4, and knowing the pressure we can then determine state 4. So that is the next step that we will be doing here. So we said S3 was equal to S4. And then we know that this is occurring at 50 kPa, and it turns out for that value we are in the two-phase region. And so those are the values off the steam table for SF, and then that would be SFG. And from that, we can then solve for the quality at state 4, 8966. So this is really a cycle that's not that great, because ideally you don't want to have expansion into the two-phase region, or you get the droplets and the drop in efficiency. But knowing that, we can then determine the enthalpy at state 4. So with that, we have all of the states specified, because we just determined state 4. So we have 1, 2, 3, and 4. And so now what we can do, basically go ahead and start applying the first law between components in order to determine the thermal efficiency. If we go back to the problem statement, they want us to get the thermal efficiency and the net power output. So we're going to work on the thermal efficiency. And we can write that the thermal efficiency is the net work in divided by the heat in. And the net work is equal to the work out of the turbine minus the work that we put into the pump. Now, applying the first law for a steady flow device with no heat transfer to the turbine and no kinetic or potential energy, that turns out to be just H3 minus H4. And then similarly for the pump, that is H2 minus H1. We know those values, so we can now substitute them. So we get that for the net work, and the heat in. The heat in we can evaluate. If we go back to our TS diagram, that's going to be what's going on in the boiler. So this is where we have Q in right here. So we're going from state 2 up to state 3 as we go through the boiler. Knowing the values of enthalpy. So there we have work net and Q in, and with that we can go back and take each of these and plug them into this equation up here. So let's go about doing that, and then that will enable us to determine the thermal efficiency of this cycle. And just like we would expect, it's not the greatest thermal efficiency. It's 28.4%. That's because we're expanding quite far into the two-phase region, and you lose efficiency as a result of that. Now, that was the first part of the problem. Let's see here. So we have the thermal efficiency. The next thing, and we wrote out the TS diagram, the next thing they want us to do is calculate the net power output. So let's tackle that. So from before, we wrote work net was 820.45 kilojoules per kilogram. The net work output is just going to be the mass flow rate multiplied by the work per unit mass that we just calculated. And what we get is that this plant has a power output of 20.511 megawatts. So that concludes this example problem. You can see it's kind of straightforward and simple, but whenever you're solving these problems, write out the TS diagram to begin with. You don't always know all the states, and so sometimes you kind of got to jump around a little bit. Had we drawn this a little differently here with expansion down into the superheated region, I would have had to have redrawn the diagram, but I made a guess that it went into the two-phase region, which in the end it did, as we could tell by the quality. But anyway, so that's the TS diagram. It came out correct in the first place. So that concludes that example problem. The next segment we'll take a look at a more challenging example problem, again dealing with the Rankine.